Welcome to this lesson, which is an introduction to electrostatics. The unique source of electrostatic field and electromagnetic field is the electric charge, which is a property of matter. Matter, in its stable state, is composed of protons, electrons, and neutrons. Neutrons have no charge, whereas protons and electrons have the same charge but with a different sign. Charge in MKS system is measured in Coulomb. The charge of the proton and of the electron is the minimum amount of charge observable in nature. Conventionally, the sign of the electron charge is negative, whereas that of the proton is positive. Therefore, on an object, the charge is necessarily a multiple of the charge of the proton and of the electron. But in our case, we will deal with arbitrary charge distributions. For instance, a point charge will have an arbitrary value of Q, and we also deal with charge densities, such as linear charge densities, ρL, measured in Coulomb per meter, which is a charge distributed, for instance, on a wire, surface charge density, measured in Coulomb per square meter, or volume charge density, ρ omega, measured in Coulomb per cube meter. If we have to compute the total charge on an object in which there is a given charge density, what you have to do is to carry out an integral of the charge density over the volume of the object. Charge density can be, therefore, a function of position. In 1785, Charles Coulomb discovered that between two charges there exists a force. Such force is attractive if the charges have opposite sign, and repulsive if they have the same sign. This expression represents the force acting on a probe charge lowercase q due to capital Q. The other parameters that are present in addition to the value of the two charges are epsilon naught, which is the permittivity of vacuum, also called dielectric constant of vacuum, which is measured in farad per meter in MKS system. The value is shown here. We have the square of the distance between the two charges, and we have a unit vector that points from the origin of the force, capital Q, to the probe of the force, which is lowercase q. If we had to express the force on capital Q due to lower q, we would simply have to change the sign of this unit vector. The various parameters that are shown in this slightly more general expression are also displayed in this picture, in which we see the position of the source charge, the position of the probe charge, and the direction of the force. If we have a different charge distribution, such as a volume density, what we have to do is to compute the elementary, the Q charge associated to this volume density, and use the previous expression. Of course, since the given charge distribution exerts a force on the probe charge Q, which is due to the whole of the charge distribution, to compute the total force, we'll have to integrate the elementary force over the volume on which the charge distribution is deployed. We can now introduce the electric field, which can be seen as a limit with small q of the force exerted on a probe charge lower q due to the source charge divided by the value of the probe charge itself. This electric field can be seen, therefore, as a vector field that permeates the whole space, but is only visible once you insert in the space a charge, because in that case the charge senses the presence of a force. The electric field due to positive charges is directed away from the charge itself. The electric field produced by negative charges, on the opposite, has field lines that are directed towards the charge itself. We see here a summary of the expression of the force due between two charges and of the electric field produced by the source charge Q, in which the important parameters are shown in this figure. The electric field is proportional to the inverse of epsilon naught, the constant we were discussing before. Therefore, if we multiply the electric field times epsilon naught, we obtain a field which is called D, electric flux density or electrical induction, which is independent of epsilon naught. The expression for D is therefore very similar, but with the the missing term epsilon naught. And also the plot in which we indicate the various position of the charges and of the direction of the D field is very similar to the previous cases. The name electric flux density is given to the following observation. Let's compute the flux of D through an elementary surface ds, on which a normal unit vector is drawn. The total flux of D is obtained by integrating the elementary flux over the whole of the surface. Now, since this is the expression of D, the total flux of D can be written as Q over 4 pi times the integral of this expression. But this expression is the solid angle seen from the position of Q and looking at the elementary surface ds. So that the total flux of D is Q over 4 pi times the total integral of the solid angle. Now, this total integral, if the surface is closed, is 4 pi. So that the total flux of D through a closed surface that encloses the charge Q equals the value of the charge itself. This is Gauss law. And for this reason, we call D flux density. In case the charge Q is placed outside the closed surface, the total flux gives 0, which is something that is contained in Gauss' law, because the previous expression that you see here, when the total charge is 0, gives 0, of course. But we can explain this by observing this figure. The solid angle that is crossed by these two lines is crossed once with the normal unit vector directed in this direction, and another time with the normal unit vector in the opposite direction. So the two solid angles and the two fluxes cancel each other. If we have in the volume more than one charge, by the superposition of effects, we have the total flux of the total D field produced by the two charges equals the sum of the charges. Now, what is the total charge inside a given volume omega? Is simply the integral of the volume density rho omega over the whole of the volume, so that the total flux of D equals the integral of rho omega over the whole of the volume. But by the divergence theorem, the total flux of a vector equals also the integral over the volume of the divergence of the vector itself, when the surface, of course, is the boundary of that volume, is a closed surface boundary of that volume. This allows us to equate the divergence of D to the charge density, volumetric charge density. And this can be seen as Gauss' law in differential form or punctual form. Thanks to Gauss' law, we can simplify a lot electrostatic problems in which we have given charge distributions and we want to compute some fields due to this charge distribution. For instance, in this case, in which we have a linear charge density in infinite extent along this direction, let's say the z-axis, we can use a cylindrical coordinate system to represent the D field. By symmetry, the D field is oriented along the rho unit vector of the cylindrical system. So that the total flux of D, that must equal the total charge inside the volume, can be easily computed because on the upper and lower surfaces of this cylindrical volume, there is no flux because D is perpendicular to the normal to these two surfaces. But on the lateral surface, we do have a flux, and in particular, the expression of the flux can be written as the surface of the lateral surface of the cylinder times the value of the D field. This flux of D must equal the total charge inside. This can be written as the linear charge density ρL times the length h of this volume along the z direction. Therefore, we have a way to compute the expression of d rho and therefore of D, produced by a linear charge density of infinite extent and constant value. The expression is given here, and it has been simply obtained by the application of Gauss' law. This concludes this lesson on electrostatics. So we introduced the presence of charges, we saw the force between different charges, we saw the electric field and the flux density of a given charge distribution.